So let's begin with the next lecture. This is lecture 13, Calculus 3. So let me start by recalling what we did last time. We were looking at conservative vector fields, and in higher dimensions, so let me quickly define the notion of conservative vector field. Recall that a vector field f bar from some region D, maybe I'll write it on the next line, f bar from D, which is a subset of R3 to R3, is conservative if there exists a function phi from D to R of class C1 such that f bar is gradient of phi on D. So in 3D I mentioned to you a theorem, but before that let me first prove a lemma that a necessary condition for a conservative vector field in R3, a necessary condition that a conservative vector field satisfies is that its curl is 0. So if f bar is conservative, then this we proved in 2 dimensions, but let me prove this result in 3 dimensions. So that is, in other words, curl of gradient of phi is always 0 for any function phi of class C1. Proof is very easy. So let f bar be gradient of phi, so which is going to be df dx, df dy, df dz, or d phi dy, d phi dx, d phi dy, d phi dz. And recall that if f bar is f1, f2, f3, if these are the 3 components of the vector field, then curl of f bar is given by, and this is a quick way of writing down the formula in a compact way, you don't have to write everything. So therefore, if you look at curl of gradient of phi, this will be I j k d dx, d dy, d dz, and f1 is d phi dx, d phi dy, d phi dz. So it's going to be let me write it in terms of the suffix notation. So it is d dy of phi x, so which will be phi of x and then y minus phi of y and then z right, phi of, I made a mistake, this is z, so phi of z and then y, phi of y and then z, I bar, minus phi of z and then x, minus phi of x and then z, z bar, plus phi of y and then x, minus phi of x then y, k bar. And now we will use the fact that phi is of class C2. So in our theorem we will need F to be conservative, but you need F to be of class C1. So if F bar is a C1 is conservative. Maybe I'll write it again. If F bar is of class C1 and conservative, then curl of F bar is 0. So because it is conservative, it is gradient, and therefore since F is C1, since F bar is of class C1, phi is of class C2. Because look, coefficients of F bar of C1 functions, but coefficients of F bar are dphi dx, dphi dy, dphi dz. So that means phi is twice continuously differentiable. So this is going to be 0 bar because phi is of class C2. So that's the proof. And so if the region D, the domain D is simply connected, then the converse is true. So this is a theorem. If in addition D is simply connected, then the converse holds. That is, if curl F bar is 0 bar, then F bar is conservative. That means F is a gradient of some function. So this is always there. The converse is also true. And this is a harder theorem, so this I will not be able to give you a proof of, but this you will study in advanced calc. So now let us see an example where when curl F is 0, we will try to see how to find phi. So in the following example, we shall see how to find phi such that F bar is gradient of phi when F is conservative. This we have done in 2 dimensions, and now the same thing, it's exactly the same procedure, but let's do one problem. So problem 1. Let's take our function F bar of x, y, z to be, let me write it as, so it's y square z plus 2xz square I bar plus 2xyz z bar plus xy square plus 2x square z k bar. So first we'll verify that the curl is 0 and all the conditions hold. So first of all, note that since all components of F bar are polynomials, all components of F bar are polynomials, F bar is of class C1 and domain of F is all of R2. So it is simply connected, that is, there are no holes. So the hypothesis of the theorem holds. Next we'll verify that this curl is 0. So next we check that f bar is conservative by checking that curl f bar is 0. So let's take curl of f bar, which is going to be I bar, z bar, k bar, and you write down the partials, and you have y square z plus 2xz square 2xyz xy square plus 2x square z. So this is going to be d dy of xy square plus 2x square z minus d dz of 2xyz I bar minus d dx of xy square plus 2x square z minus d dz of y square z plus 2xz square z bar, and plus d dx of 2xyz minus d dy of y square z plus 2xz square k bar. So if you just calculate this, you will see you are going to get 2xy, the partial of this with respect to y is 0, and here you get minus 2xy I bar minus partial with respect to x gives you y square and then plus 2. What is this term? Let me just double check. This is going to be xy square plus 2x square z. So when you differentiate this with respect to x, you are going to get (4xz) minus partial with respect to y gives you minus y square, and then here 2xz square will give you again minus 4xz z bar plus partial with respect to x of the last term is 2yz minus here partial with respect to y is going to be 2yz k bar, so which is 0 bar. So therefore f bar is conservative. So now we want to find phi such that grad phi is f bar. So therefore you want d phi dx to be your m. So I write f is equal to mi bar plus nz bar plus pk bar. So this is going to be y square z plus 2xz square. D phi dy is 2xyz and d phi dz is xy square plus 2x square z. So we'll follow exactly the same procedure. Therefore I start with the first one and integrate. Phi of xyz will be integral of the first component of f with respect to x plus some function, but this function now will depend on y and z, psi of yz. So this is going to be, when you integrate it, you are going to get xy square z plus integral of 2x z square with respect to x will be x square z square. 2 and 2 in the denominator will cancel, plus psi yz. Now you use, so let's call these 3 equations. So we have used this. Now we use the other one. So now use d phi dy to be, we know it's 2xyz, so we use this. So d phi dy is going to be 2xy plus partial of psi with respect to y, and that must be equal to, have I done this right? D phi dy is going to be, I made one mistake, I forgot the z here, so it is d phi dy is going to be 2xyz, that must be equal to 2xyz. So that gives you d psi dy to be 0. So psi depends only on z. Psi of yz is just psi of z. Psi depends only on z. Now use the third equation. Now use d phi dz equal to xy square plus 2x square z. So we know that phi of xyz is xy square z plus x square z square plus psi of z. So d phi dz is going to be, we'll get 2x square z plus d psi dz, right? And that is equal to let me double check everything. So this d phi dz is going to be I keep on forgetting there is a z here, isn't it? D phi dz, when you take, what is our phi? We found out phi to be this. So when you differentiate with respect to z, I get xy square plus 2x, yeah, so plus 2, I forgot that. I need to differentiate this. There is a z here, so I get d phi dz equal to xy square plus 2x square z plus d psi dz, and that's equal to xy square plus 2x square z. So that tells you that d psi dz is 0, therefore psi is 0, or a constant, it doesn't matter if you add a constant. So phi of xyz therefore is going to be xy square z plus x square z square. Good. So you can see now that the gradient of this phi is f. So this is exactly the same procedure that we did in two variables, how to find phi. So thus the method of finding phi so that f bar is grad phi is exactly as in the case of two variables. Once you know that the vector field is conservative, then it's exactly the same. So now let's move on to the next topic, and the next topic is called Green's theorem. There are two forms of this theorem, and I will explain first the first form. So what does this theorem say? So let's take again a function which is of class C1 on a region D. This is for 2D, so I will mention this theorem only in 2 dimensions. Okay, so let's take this be a C1 vector field of class C1, and say f bar I write as f of xy is equal to mxy plus I bar plus n. Let me put the pen for a little kick. This pen is doing funny things at times, so I need to. It was actually charged just before this lecture, but it needs a little push in between, so now it will work, I think. Plus nxy is a bar. So here is a picture. Here is my D, and I have a closed curve. Maybe I'll do it like this. This is my D, and I have a closed simple curve inside inside D. So let C be a closed simple smooth curve inside D. Then we are going to say the line integral of f bar on this curve oriented anticlockwise is equal to the double integral for on the region, maybe I'll call, D is the domain of the function. It's better if I call the region enclosed by this curve R. So it's the region R over which you integrate the function dn dx minus dm dy. This function will have a meaning. Later on we'll see that this measures something which is called the circular density, this function at a point, but we will worry about that later. So this is an important relation between a line integral and the double integral. So if you have a region R which is enclosed by curve C, then the line integral of a C1 vector field along the curve equals the double integral of dn dx minus dm dy, where f is given by mi bar plus nj bar. So this is one of the important theorems of mathematics. And we will first see, I will talk about why this is so and so on little later. First of all, I will verify. So our next problems are going to be on verifying Green's theorem. So let's do problem 1 on Green's theorem. Let us take a function f bar of xy to be xi bar plus yj bar, and let R be the region inside the unit disk. So your R is going to be all points xy for which x square plus y square is less than or equal to 1. So here is a picture, and the problem is verify Green's theorem. Form 1. I'll tell you about form 2 later. First, let's practice with this. So what you will do is calculate the integral on the left, the line integral, and calculate the double integral, and we'll see that they are equal. So we compute integral f bar dot dr bar over c. So we'll need to parameterize c. So c is r bar t given by cos t comma sin t. This is a natural parameterization of a circle. T goes between 0 to 2 pi. So r bar prime, that's what we'll need, is minus sine t comma cos t. So this line integral f bar dot dr bar over c is going to be integral 0 to 2 pi f bar, which is, or f bar is what? X comma y dot minus sine t comma cos t dt. So this is going to be integral 0 to 2 pi. Remember, x is cos t, y is sine t. So this will be integral cos t comma sine t dot minus sine t comma cos t dt, which is integral 0 to 2 pi minus cos t sine t plus cos t sine t dt. So this is going to be 0. Now let's compute. Now consider double integral on R of the vector field of dn dx minus dm dy. So what was n and m? M was, m of xy was just x, n of xy was y. So therefore dn dx minus dm dy is just 0. Therefore double integral of 0 dA is just 0. So thus both sides are equal. Both sides in the above formula are equal. So we have verified Green's theorem. Let's do one more. Verify Green's theorem. Where f bar of xy is given by 5xi bar. This pen has some funny problem. Let me give it a kick. Yeah, okay. 5xi bar plus 3yz bar. And R is described as follows. Described in the graph, in the picture, in the sketch or figure. So here is a picture. You take a circle of radius 1. Hold on. Take a circle of radius 1 with center at 1 comma minus 1. So this is C is the circle x minus 1 square plus y plus 1 square equal to 1. Good. And R is the region, R is the disk xy such that x minus 1 square plus y plus 1 square is less than or equal to 1. So let's verify this. So first of all, we'll need to parameterize C. So we need to parameterize C. And how will we do that? That's not difficult because a circle, you see, x is going to be, the center is 1. So x minus 1 is cos t. So x is 1 plus cos t. Y plus 1 is sin t. So this is y minus 1. Y is minus 1 plus sin t. That's a parameterization. T runs between 0 to 2 pi. So you want x minus 1 to be cos t and y plus 1 to be sin t. So therefore, r bar t is going to be 1 plus cos t, comma minus 1 plus sin t. This is a parameterization. You can, and then you can take the derivative. This is minus sin t, comma cos t. So now let's calculate line integral f bar dot dr bar over c. It's going to be integral. My f is 5x, x is 1 plus cos t, comma 3y, which is 3 times minus 1 plus sin t, dot product with minus sin t, comma cos t, dt, 0 to 2 pi. So let's see what that turns out to be. So this is going to be integral 0 to 2 pi, 5 times 1 plus cos t times minus sin t plus 3 times minus 1 plus sin t dot cos t dt. So let's simplify this. This is going to give me, without, hopefully without any error, let's see what we get. So you get minus 5 sin t, then you get 5 minus 5 cos t sin t, then you get minus 3 cos t, and then you will get plus 3 sin t cos t. Good. So let's see what that turns out to be. So this is going to be, now if you integrate cos t and sin t, this is going to give you 0, isn't it? Because this will be minus 5 cos t, integral of sine is minus cos, so this will give you plus 5 between 0 to 2 pi. Similarly, the other one will give you minus 3 sin t, 0 to 2 pi. And these two quantities will add up to give you minus 2 sin t cos t integral 0 to 2 pi dt. So this will turn out to be 0 minus 0 minus, and if you know your double angle formula, this is just sine of 2t. So this will be cos 2t by 2, 0 to 2 pi, and that will be 0 because cos is periodic with period 2 pi. So line integral turned out to be 0. Now consider the integral over r of dn dx minus dm dy. Well, what was our function? So you see that again dn dx is 0 because f bar was what? 5x bar xi bar plus 3yz bar, right? So n is 3y, so dn dx is 0, dm dy is also 0. So this will be 0. So thus Green's theorem is verified. Good. So now I will tell you the meaning of the right hand side, and that is, so now we consider why should, so let me give some explanation of understand. So let me word it like this: understanding the meaning of this quantity dn dx minus dm dy at a point xy. And then once you understand this, you will see the idea behind the proof. And the idea behind the proof. So let us see what this is. So you have a region and you have a curve, and then we are going to now see what this quantity turns out to be. So let's take a typical point, maybe. In fact, if you are taking, so we are taking any typical point xy in the region R, and now I go tiny, let's take a little tiny rectangle x. So the components are, I mean the coordinates of these corners are xy, x plus h, y, x plus h, y plus k, and here it will be x coordinate is the same and y plus k. And let's calculate the line integral. So let us find the line integral of f bar on this little curve C, where C is a boundary of a rectangle with vertices xy, x plus h, y, x plus h, y plus k, and x, y plus k. And you will see what we want to do is we want to compute this particular thing, which is like calculating the work done in taking this point around a little rectangular route. And then we will see that if you divide it by the area and let the area tend to 0, that gives you the quantity dn dy minus dm dx. This is called the circular density. We'll get to that in a minute. So the integral of f bar over C, f bar dot dr bar, is going to be, and now I'm going to make an approximation assuming that this rectangle is very tiny. I make the assumption, so you remember the definition of line integral is the work done by the force. So it's the force multiplied, so you will take this force f bar, I'm going to take its component in the I directions, because here your R bar is along the I bar directions. So I will take the component of f bar at xy dot I bar times the length through which the particle moves. So that's your integral on the first piece. Integral on the second piece, so this is going to be line integral on, shall we call these, let's call these ABCD. C is a bad choice because C is also for the curve, but in anyway we'll not get confused. So the integral here, so let's write this as integral over the piece AB is going to be f bar xy dot I bar h, which is going to be m xy h. Integral over the piece BC is going to be integral on that piece is going to be f bar at x plus h comma y dot z bar times k, which is going to be n at x plus h comma k, x plus h comma y times k, integral on CD is going to be integral minus of integral on DC, and minus of integral on DC will be f bar at x plus h comma k, x plus h at this point, x comma y plus k. So it is x comma y plus k dot minus sign dot z bar, and then the length will be h. So this is going to be minus m at x y plus k times h, and the integral on dA will be minus integral on AD, which is going to be f at xy dot the z direction, so in the last, here it is I bar of course, and the last one is z bar minus sign, and that times the length, which is k. So this is going to be n xy k. So if you look at this integral of f bar on the curve ABCD, this is going to be, we'll have these four terms added together, which we will write as you can see, this is going to give you n at x plus hy minus n at xy times k plus m, or I will put a minus sign out, so minus m at x comma y plus k minus m at xy times k times h. But you see, by mean value theorem, this is exactly going to be approximately dn dx times h times k minus, so I will write a little twiddle, means approximately this is the same in the limit when your partition is going to tend to 0, meaning if your rectangle, your h and k are going to tend to 0, then the error term will tend to 0. So you can equate this. So this is going to be dm dy times k multiplied by h. So what happens is, if you take this integral of f bar dot dr bar, this is what you would like to call circulation around, or circulation as you move in this loop, circulation when we move on the boundary of this rectangle. This is going to be dn dx minus dm dy times hk plus some error terms. Error terms because you will have, because of the one more time, this pen is today acting up. The error term comes from the fact that in mean value theorem you have the higher order terms. So the higher order terms will not matter when you take the limit as h and k tend to 0. So therefore now I want to introduce the concept of, so you will take 1 over hk times f bar dot dr bar over abcd. This quantity will be dn dx minus dm dy plus error terms. Error terms will be in higher order of h and k. So error terms will be of the order of, I'm giving you a sort of no, I mean the idea of the proof is correct. It's not written completely precisely, but that is where you will need Taylor's theorem. So these are of the order of h square k square. So as hk tends to 0, h comma k tend to 0 0, this average 1 over hk times this integral on this loop ABCD will tend to dn dx over minus dm dy. So this gives you the meaning of this quantity. So therefore dn dx minus dm dy at any point xy is called the circular density of the vector field. Of f bar at xy. And so when I told you that when you are talking about curl of a vector field, remember this is just the kth component, I mean the third component of the curl. When f is in 3 dimensions, this is just the component that goes with k bar. So there I mentioned that the curl of a vector field captures the rotation which is inside this turbulent fluid, if you think of f bar as a turbulent fluid. And here I gave you the explanation why it measures the rotation. So this quantity dn dx minus dm dy is called the circular density. And now you can see what's happening. Now you can get a sort of intuitive understanding of the theorem. The theorem that we have written, Green's theorem, says that if you take at each point there is a circular density which is dn dx minus dm dy. If you integrate over all these points, then you get the average circular density, and the average circular density actually equals the circular density on the boundary. So Green's theorem says that the total circular density of f bar in the region d bar, in the region R equals line integral of f bar dr bar over c, which is the line integral of f bar on the boundary of R. And a way to think about the proof is you chop this region into small rectangles just by taking a partition, as we did this when we define integrals. And if you chop this into finite partition, very small partition, then you look at each rectangle. Forget about the rectangles which are at the which are not rectangles but which are at the edge. The other rectangles, if you calculate the circular density, the right hand side, dm dx, dm dy, you calculate the double integral, things will cancel and you will only get the integrals around the boundary. And that is how the proof goes, that there is a cancellation when you take the integral of this quantity, which will be equivalent to calculating the line integrals on each of these little squares. The total sum of that will be exactly the one on the boundary. So roughly that is the idea behind this proof. So this is a very important and deep theorem of mathematics. So this is the second important theorem in this course. The first one you have seen is the fundamental theorem of line integrals. Now I want to mention the second form of Green's theorem. And for this, I will introduce first of all the concept of flux integrals. So first we will see the concept of flux integrals along a curve. So we have the following situation. You have f bar is a function, is a vector field in R2 and be of class C1, and C, which is t goes to R bar t, be a closed curve, be a not closed, be a let me call, say t is between A to B, be a smooth curve in D. Then the flux integral of f bar along curve C, denoted by, you put a little circle there, f bar dot n bar ds. So remember, line integral was f bar dot t bar ds. So this I will define in a minute. So denoted by this is given by, is defined as follows. Let me define it more precisely. So what you do is you take n bar, the outward normal. So you have a curve, you have a point r bar t, and when you talk about the capital N bar, remember tangent vector is here, the unit tangent vector, unit normal vector is like that, which we call n bar, and what we want is unit normal vector in the outward direction. N bar be the unit normal, outward normal. That's the way I should define it. Unit outward normal vector. So the usual vector is, so capital N bar, remember, is going to be given by, we are in 3D, we are in 2D, so you have t bar, n bar and k bar. This forms a principal triad. So you know that k bar cross t bar is n bar. So little n bar, the outward normal, is going to be t bar cross k bar. And if you write this down, this is going to be I j k. My t bar is going to be, let's call this curve xt yt. Z is 0 because we are doing two-dimensional thing at the moment. So it's going to be x prime, y prime, 0, and then you have 0, 0, 1. Of course, I have to divide by the norm, so maybe I divide it by the norm of r bar prime at a general point. So this is going to be my n bar. So it's going to be 1 over norm r bar prime t. And then if you calculate this, this is just going to be y prime I bar plus minus x prime z bar. So therefore, f bar dot n bar ds integral will be integral, the function f is m I bar plus nz bar. It's dotted with y prime I bar minus x prime z bar. There is a r bar prime t in the denominator, and ds will be norm of r bar prime t dt, since ds is norm r bar prime t dt. So this is going to be integral m y prime plus minus n x prime dt. R bar prime cancels, and this will go from A to B. So this is the formula by which flux integral is defined on C. So the idea is the following. Now you think of D, your domain, and the vector field F as D as a kind of turbulent fluid. And what we did when we looked at integral, let me compare. Integral f bar dot dr bar was just integral m x prime plus n y prime dt from a to b. And the flux integral is m y prime minus nx prime. And the flux integral tries to, in physics this has a meaning. It is, if you think of this as a fluid, it's the fluid oozing out in the normal direction at the point r bar t. That's this quantity. And you are integrating it over the entire curve. That means if you think of this as a turbulent fluid, this is the flux in the perpendicular direction, the fluid passing through this curve in the perpendicular direction to the other side. Yeah, so in physics, integral f bar dot n bar ds on C is thought of as the flux of the fluid. So you think of f bar as a force acting at each point x, y, z of a fluid particle. Then this is the flux across the curve C. So this is a physics interpretation of flux integral. Now let's calculate some flux integrals. So let's do some simple problems. So example 1. I will call it example, it doesn't matter. Let's do the same problem that we did. Take this vector field and let's take the circle, unit circle, and let's calculate the flux across C is the unit circle, oriented counterclockwise. So r bar t here is going to be cos t sin t. T varies between 0 to 2 pi. Good. All right, so therefore, let's calculate the flux integral f bar across this curve C, f bar dot n bar one sec, because again the pen is, my stylus pen is not working properly today. I have to check why this is happening. Let's see if it works now. So integral f bar dot n bar ds is going to be integral, remember, my prime minus nx prime dt between 0 to 2 pi, and my m is x, so this is going to be, and x is cos t, so this is going to be cos t times y prime is, this is your xt yt, y prime is sin t's derivative, which is cos t, minus n, which is x, which is cos t, times x prime, which is minus sin t dt. And this is going between 0 to 2 pi. So you see that this is going to be cos square t plus sin, cos square t plus, I made a mistake, isn't it? Because my n is y, which is sin t, so that's going to be sin t. So it's going to be cos square t plus sin square t dt. 0 to 2 pi, which is going to be integral 1, 0 to 2 pi, which is 2 pi. So the flux flowing, when you think of this as a fluid, every point is being acted upon by this particular force in this direction at any point xy, then this is the flux across this closed curve. All right, so that's example 1. Let's do the flux. Let's calculate also the flux in our second example. In that example, our circle was like this. So your curve r bar t was, if you remember, 1 plus cos t, the parametric form, comma, minus 1 plus sin t, t between 0 to 2 pi. And my vector field was 5x I bar plus 3y z bar. So let's calculate the flux integral of this vector field. So let's write this as this dot n bar ds over c. That's going to be integral 0 to 2 pi. My m is 5x, x is 1 plus cos t, times y prime. This is my xt and this is our yt. So y prime is cos t, minus n, which is right, isn't that? Yeah, so this is m y prime minus nx prime. So n is 3y minus 1 plus sin t times x prime, which is minus sin t dt. So this is going to be integral 0 to 2 pi. Let's double check. 5 times x, which is 1 plus cos t, times y prime, which is cos t, minus 3 times n, which is minus 1 plus sin t, times x prime, which is minus sin t. Okay, so what will that give you? It is 5 cos t plus 5 cos square t, and then you will have minus minus plus, plus times minus 1 is minus 3 sin t. Good. And then you will have minus minus times this is plus 3 sin square t. Good. So this integral, first of all, integral 5 cos t and minus 3 sin t, that's going to give you 0. Plus, I will add 3 cos square to 3 sin square. So I will have integral 0 to 2 pi 3 dt. And what is left is 2 cos square t. So this is going to be 0. This is going to be 3 pi. Good. And so let's see what's going to happen. And then we want to integrate 2 cos square t. Well, you use double angle formula to integrate that. So this is going to be, so maybe 0. So this is going to be 0 plus t pi, 3 pi, 3 times 2 pi, which is 6 pi. And then you will have, remember, cos 2 theta is equal to 2 cos square theta minus 1. So 2 cos square theta is 1 plus cos 2 theta d theta between 0 to 2 pi. So this is going to be 6 pi plus 2 pi. Because the integral of cosine 2 theta will be 0. So the answer will be 8 pi. So you need to practice with evaluating the integrals, the flux integrals. I did 2 examples. Now I want to mention the second form of Green's theorem. So it says that in the same hypothesis, so you are taking the same thing, same hypothesis, so let me not write it. So F is a C1 vector field, and then you have a region D, and you have a simple smooth curve which traps region R. C is counterclockwise. Then the flux integral of F bar dot n bar ds over the curve C is going to be the double integral of the quantity dm dx plus dn dy dA. So line integral equals, what we saw is the right hand side dn dx minus dn dy was the circulation density. This we will see has also an independent meaning. It will be called the flux density, but we will do that next time. At the moment, let us just verify. So let's do problem 1. Verify Green's theorem, second form, for F bar equal to xi bar plus yj bar on the unit disk, and C is the unit circle. So we actually calculated this, didn't we? We calculated the flux integral just a while ago. So we saw that flux integral of this vector field around this curve is equal to, the first example came out to be 2 pi, isn't it? Yeah, that was 2 pi. So let us now compute the double integral on R dm dx plus dn dy dA, and this is going to be just 1 plus 1 dA, which is 2 times the area of a unit circle, and the area of the unit circle is pi r square. R is 1, so therefore Green's theorem holds, because it has to hold. We have just verified, so therefore Green's theorem is verified. Let's do problem 2, where my F bar will do the same problem we just worked out before, 5xi bar plus 3yj bar, and your curve is this circle centered at 1 comma minus 1. We saw that the flux integral of this vector field was 8 pi, and let's calculate now we find double integral on this curve of dm dx plus dn dy dA. This is going to be double integral. Dm dx is 5, dn dy is 3 dA, and the area of the region is pi, so it is 8 times dA over R, which is 8 pi. So again, Green's theorem is verified. So let me write down both forms of these to summarize. Let's see what we have said. We have said that line integral of F bar dot dr bar, or maybe I'll write it in the form T bar ds. This along a curve C is equal to the double integral of dn dx minus dm dy over R, and this is your form 1. And on the other hand, the flux integral is dm dx plus dn dy dA. This is form 2. So these quantities have a meaning. So dn dx, as I told you, dn dx dm dy at the point xy is circulation density, and we will see next time that this quantity dm dx plus dm dy at xy is called the flux density. It's in some sense like you have a turbulent fluid, and at each point you take a little rectangle and you want to find out how much is oozing out divided by the area, how much of the fluid is oozing out, divide by the area, take the limit as this area tends to 0, that limit is this quantity. So math captures that. And now we will see the remaining part of the course is how to see the analogues of this in higher dimension. So there is an analog of both forms of Green's theorem in R3, and these are respectively called Stokes theorem and divergence theorem. These are respectively Stokes theorem and Gauss's, or it's also called divergence theorem. For this we'll have to learn triple integrals. So what we are doing now was for pancakes. Now you have to do it for a more general solid. And so for that you will have to know how to integrate on a solid and how to integrate on its surface. So for this we shall need two more concepts. One is concept of triple integral integrating over volumes, which is an analog, three-dimensional analog of double integral, and then something called surface integrals, which is the analog of integrating along a curve in 2D. So now in 3 dimensions you will have a surface and you would like to integrate on a surface. So that's why Calc 3 is not an easy course, because you have too many new ideas and you need to compute with this and get an ease, and so in your computation in a short period of time. But anyway, so I will end it here. Next time I will tell you why this quantity flux dm dx plus dn dy has a meaning. It's called the flux density. So you have two things, circulation density and flux density, and the analogues in 3D will be the idea of curl and divergence. I'll introduce this next time.